to the first class, and we'll just flip through the PowerPoints real fast. So basically, I think chapter 1 talks about the basics of a PLC. Are y'all okay with that? About the memory and the makeup of a PLC. So what's the basic components of a PLC? Start with the main guy. Got to have power supply, right? Got to have a CPU. The processor is part, and it's strange the way different things change when you go through different disciplines. So we call the actual little computer, we call that a CPU. When in actuality, it is a computer. And then the CPU is the processor that's inside. But just over time, that's what everybody calls the actual whole computer. They call that the CPU. So we have the CPU. And then what else do we have? Power supply, CPU, inputs, and outputs, right? And that's pretty much, well, the makeup of the PLC. Now we can take those and we can do it as a modular, which means what? We have a power supply that is separate from the what? CPU that's separated from the input-output line. Then we can have what we call a fixed PLC, which is what the 1000 is over there. And what's that? And what advantages does a modular PLC have over a fixed PLC? You can upgrade it, right? You can change it. It's easier to repair. So a fixed PLC, if I lose one of my inputs and I have to have that input, which you shouldn't do, by the way, you should never buy a PLC that has exactly the number of inputs that you need. Why is that? Because you lose all your expandability. If you lose one, you got to replace the whole PLC. If you have extra inputs and you have extra outputs, then what can you do? You can move it and then change your programs, right? And that would be a lot cheaper than trying to buy a new PLC. So modular PLCs are easier to repair. So if you lose an input module on a PLC, instead of replacing everything, you just can do what? You can just replace the module. If you need to upgrade it, if you need more inputs on the modular PLC, then what can you do? You can buy another input module. If you need more outputs, then you can do what? You can buy another output module. So the big advantage of modular PLCs is they're very expandable and they're easier to repair or cheaper to repair. They usually cost more up front, but they cost less to keep running, right? You understand? It's just like transformers. A three-phase transformer costs less than if I was to buy 3 transformers, single-phase transformers, and wire them as 3-phase. It would cost more. But if one of my windings go out on a 3-phase transformer, I have to do what? Buy the whole transformer. If one of my transformers go out and I use these individual transformers, then I can do what? Now I can just replace that one transformer. So just about every place you see that runs 3-phase, they'll actually use 3 individual single-phase transformers that are wired 3-phase. So a modular PLC is more expensive up front, right? You understand? But it's what? It's cheaper to maintain. A fixed PLC is you get what you pay for, right? You understand? It's very what? You can't do what? Expand it, and it's hard to repair. All that makes sense. So if I lost the CPU on a modular PLC, then I could just change that CPU module. If I lost the power supply, I could just change that out. If the power supply goes out in a fixed PLC, then what? Yeah, and these guys are not repairable guys. So what they're doing now, just about all your PLCs, is what I refer to as hybrid PLCs, which is what? You can add to them, yeah. So what you can do is you get a certain number of inputs, you get a certain number of outputs, and then you got a way you can slap additional modules onto the side on a rail system, usually what we call a DMARC. Everybody okay here? So that's basically what we went on chapter 1. I think they talked about Scan. Everybody else okay with scan? So what is a scan? A PLC scan? It's the time it takes to go through what? The program. And how does it work? Top to bottom, left to right, right? Inputs. Not yet. Input, process, output. You understand that? It scans inputs first. Then what does it do? Then it processes it. It processes the instructions, and then it develops outputs on what the instruction says. PLC selection. That's what Phil's talking about. We've already talked about that. Numbering systems. Everybody okay with numbering systems? We're going to be using numbering systems in this class. When we start doing masking, you know, what do you think masking is? So when you put on a mask, what do? You cover up. You let people see what they want to see. Well, with masking, what we have to do is we can take a big binary number and we can strip off bits, or we can add bits, right? Using mask. So I could load in 16 inputs, but I'm only concerned with what's going on with input 4. Well, what could I do? I can mask off everybody else, right? You understand that? So we'll learn about masking. So we got instructions that do that for us. We have move instructions. We have move with mask. So I can actually take a number and I can mask it before I move it somewhere else, right? You understand? Strip off things. ORs. We have ORs. Logic ORs. So right now we know we can OR with contacts, but we can also OR. That would get very cumbersome if you had to OR 16 inputs. That means you'd have to put 16 inputs what? In parallel. Wouldn't it be nice if I could just bring in that whole 16 bits into a register and then OR it with, right? You understand, with something with 16 other things? Well, the problem is that you got to understand what? Binary. Well, you got to understand binary, right? You understand that. And logic. So and logic. We can and stuff. We can complement or negate or not. So that's a term we use. When we use the term complement, that complement means the opposite of. It don't mean I'm going to say, well, you look nice today. In digital computers, if we say complement, it means we take the opposite of. So when I compliment y'all, you said, well, Rich is taking the opposite of, right? So to do that, you got to understand binary. You got to understand. So when I do logic, I got to do that's binary or hexadecimal. So we'll learn how we can enter numbers in different bases, even though we talked a little bit about it in Intro to PLCs, how we can enter numbers in different bases. We'll look at that in a little more detail. So anytime we do logic, like in what's the logics we have? We have and, or, NAND, NOR, not, exclusive OR, and exclusive NOR. Those are the objects. And it's kind of strange. We don't have a NAND, and we don't have a NOR, and we don't have an exclusive NOR. But we've got a complement. So what you'll do in this class is, if you need a NAND, you will AND it and then do what? And then invert the answer. So it'll take two instructions to do a NAND. So we don't have an exclusive NOR because we can do what? We can do an exclusive OR and then just complement the results, right? You understand? And we'll see how to do that. So yeah, if you look at the instruction set, you won't see a NAND NOR, you won't see a NAND NOR, but you'll see a NOT, right? And when we use these instructions, we're dealing with multiple bits, and we're ANDing that or ORing that with another multiple bits. Everybody okay on a bit? Y'all understand bits? Y'all understand bytes? Well, we had several people in PLC 1 that didn't know what a byte was. It was on the filings, eh? So what is a bit? One single binary digit. Oh, yeah. So I said, what's a bit? And he said it's a bit, so one single binary bit, right? It's one single binary digit, and then what's a nibble? It's a group of 4 consecutive. You can't just start anywhere. We start them from the least significant bit. Everybody understand that? And what's a byte? It's a group of 8 consecutive bits, starting from the least significant bit. Everybody understand that? So you just can't grab 4 bits with a big number and say, well, there's a byte. It's always referenced from where? The least significant bit. Then we have what we call and then you start counting in 8s, and then you put a line, right? Then you start counting 8, and then you put a line, and then you're dividing the big number into bytes. If you're dividing it in nibbles, you would start with the least significant bit, you would count off 4, and then you put a line, you count off 4, and put a line. We do that, of course, going through hexadecimal, right? You understand that? And also BCD. We had problems with BCD. For some reason, once we teach BCD, people have a tendency to believe they can go from BCD, BC to binary, or from BCD to binary by using groups of 4s. You cannot do that. Or going from decimal, they think they can go from decimal directly to binary by splitting it up into groups of 4. And that's not true, because the C in BCD is a what? Code. We can go to hex for binary by using groups of 4s, and we can go from binary to hex by groups of 4s, but we can't go from decimal to binary by using groups of 4s. Everybody understand that? You cannot do that. So if I do that, then I'm actually going to BCD. So we're going to look at that. Everybody okay with that, though? Then the next one is I/O. Everybody okay with I/O, input outputs? And motor controls. So ladder logic, to understand ladder logic, we have these rules, and I'll print those off and give them to you. The book doesn't do a really good job on the rules, especially on the number of output devices that we can have in a rung. So one time it says in the rules that you can only have one output per rung, which is wrong. And then later on it says if you have multiple outputs, you have to put them in what? Parallel. So that's a big problem. So what we did is we learned that in PLCs or in motor controls, we don't deal with rungs. What do we deal with? We deal with lines. So every line gets a number. We don't number rungs, we number lines, right? Everybody understand that? And the rule is that the actual rule is what? 1 rung per line. Everybody understand that? 1 rung, 1 output, I didn't say it right. 1 output per line. But we can have multiple outputs per rung. So everybody understand what a line is? Yes or no? So this is the one that we usually show. This is the U.S. Steel print. So this is actually from U.S. Steel. So any horizontal line that lines up, so these 2 lines right here are in the same plane, so they get the what? They get the same number. Everybody understand that? Now look how many outputs. Look how many outputs this guy here has. So this rung right here has 1, 2, 3, 4, 5, 6 outputs. Right? But every one of them are on a different line number. Now here we got a line number that's stuck out here in no man's land. It looks like it. But this guy right here lines up in that plane, right? Understand that? So every line that's in the same plane gets the same number. What about the one above it? That's a different rung. Yes, I can.
So that one that's coming down, while we open the different wrong, coming down parallel right there.
No, this is the same rung, but it's not. Yeah, right. Yeah, I didn't see that. Thank you. Okay. Also, the book says if you're going to put comments, you need to put them on the right-hand side. But in actuality, comments can go. You'll see them on both sides. So what they're doing here is they're defining all the mnemonics that we use. So what you do on your output call, you give every one of them a name. Now over there in PLCs, we use little names like CR, M1, M2, but in life you're going to end up with a ton of motor control. So what they do is they assign these things these little mnemonics. Now mnemonic starts with an M, even though we start with, so the M is silent. I feel sorry for people coming in trying to learn the English language. Because we have silent letters, we have, it's weird. We have we have words that mean the same thing, different things, like resume and resume. Left and left behind, right? So, weird. So, a mnemonic is a memory jogger. It's usually something, so if you try to remember somebody's phone number and you just remember something cute about them, a lot of times and it's something real short. Normally it's kind of like an abbreviation. So these are mnemonics over here, 5B, 1D, 2D. So I've been working on this thing, so I know this would be number 5 bridle, number 1 dynamic braking coil. But what they also do is they come over here and do what? They define the mnemonics for us. So those would be comments about the run. Normally these guys don't fit anymore. So what they do is they write the name above the coil, which is what what Allen Bradley does, or RS Logic, when you give it a symbol, right? When you give the symbol a name, it puts it above the coil. And and then comments, Allen Bradley comments will go above the rung. So if you put a comment on the rung, it goes above the rung. If you put a comment about the coil, I think it goes above the coil. What RS Logics does, it'll display symbols, which Siemens calls tags, by the way. It displays those in green, and then it displays comments in yellow, with a yellow background. Yes, I forgot. I usually set my alarm. Everybody okay here? Now what's these over here? This is what we call, they're called numerical cross-reference numbers, and it tells us the location of every coil's contact. And what's this over here? Yeah, this tells us a page number, then this tells us a line number. So can y'all see that? So this says 137.2, and this says this contact. So if I look in line 2, there it is right there. Y'all understand that? Yes or no? Then it says it's underlined. What does the underline mean? It means we're looking for a normally closed contact, right? This says this normally closed contact is in line 57. And guess what? I don't have 57. But if I did, that's where it would be at, right? You understand? And this is electrical controls. What don't we get in PLCs? We don't get numerical cross-reference. We do get symbols. Like I said, Siemens calls them tags. And it's kind of misleading. It's not actually symbols, it's symbol names, right? You understand? So this is a symbol right here. So in Allen Bradley, when you're assigning a symbol, you're actually assigning a symbol name. You're assigning a name to that symbol. Y'all understand? And what's nice about symbols, symbol names, is that once we assign a symbol name to a device, then instead of remembering that logical address, we can use what? We can use the name, which is pretty neat. Everybody okay? Okay, 30-minute break. 30-minute lunch, right? Coming back here. Yeah, we'll be here the rest of the day.
No, we did 1:30 for the,
Was that?
start the last one. We gotta go start at 1:30.
Yeah, I know. We just might have to make y'all finish it up on Friday. Since y'all doing that, we can justify it.
Thank
Oh wait, is not supposed to be in on this?
I don't know.
I've got one class.
Well, yeah, you should be up
You
there.
didn't apply for graduation?
I thought I did.
You should be up there. Get an email about, it's a
let me
mandatory
check.
meeting. So today is the last day for investment. Tomorrow there's one in Birmingham. So if you don't make today,
So what's the first thing you do when you create a program? What's the first thing you do when you connect to a new PLC? Huh? Huh? So we played around with this a little bit. Well, the first thing you do with the new PLC is you got to establish the communication between your computer and the PLC, right? You understand? So Rockwell puts out a application called RS Links, and that's where you go in and you set up what driver you're going to use. So what's a driver? Not the people that drive people around. In computers, what is a driver? So it's a piece of software that controls a specific hardware device, right? So right now I'm using an operating system. An operating system, what is an operating system? An operating system is the system that makes the computer operate, right, period. Because a computer can do one thing. What's the one thing a computer can do? Run programs, right? You understand? So we have to have a program in that computer that makes it do everything. So everything you see your cell phone do is ran by a program. Then we have what we call an operating system, and then we have applications. So what's the difference between an operating system and application? An application. We have apps. Download that app. I got to download that app. Right? You understand? That's a free app. That's a free. What is an application? That's short for application. What is an application? It's a program that applies the operating system to perform a task. You understand that? So an operating system consists of hundreds of drivers. And then it's got something that allows you to control the operating system that we call the shell. So when I load in an application does not have drivers. Because if that means so I've got an iPhone 5, right? You understand that. But I can download an application now because that application does not have the drivers that make my iPhone work, but it applies the drivers that's already there, right? You understand? So mine's probably got a different display on it than a new 8, right? You understand that? But the problem is it makes no difference because the application does not have the display driver. The application just says, I want to display this, right? You understand? And it uses the drivers that's already available. So an operating system is just a conglomerate of drivers that make the computer operate, and then it's got some shell that allows you to control that. So when you pick up your phone and you look at it and it's got that nice screen on it, you're looking at the shell. Most of our shells now are what we call GUI. GUI. What's GUI? Anybody know what GUI is? Graphical User Interface. Yeah, so our shells now are GUI, graphical interfaces. Originally they were text-based, but now they moved in. And what's interesting is a lot of your robots still use text-based interfaces. Your programs are going to be in text. So we okay? How'd we get off? We okay? So first thing we do when we get a new computer, or not a new computer, when we got a new PLC, and then we got a computer, the first thing we do is establish our communication with that device. So RS Logic provides something called RS Links. So it's in the Rockwell software. And then, of course, what we do with RS Links is this is where we establish the communication between our computer and the PLC. I don't have anything connected up right now. But this is where you configure the drivers and install the drivers. So the drivers that RS Links support is up in here, available driver type. And I have 2 drivers installed. But these are every one that's available to this, right? You understand? Okay? And then once you install a driver, and then what you do next is you configure the driver. This shows us which port it's using. It shows us the baud rate. Yeah, and it's kind of misleading. Originally, it was the number of bits per second, and it's still true on the old RS-232 interface, which is what this guy is. So this means right now, and this is the fastest interface that RS-232 supported, was 19.2 or 19,200 kilobits per second. But what's happened with baud rate now is baud rate is the number of transitions of the carrier. And then what we do is we modulate the carrier to carry the amount of information. We got several ways we can modulate the carrier that we won't get in. Yeah, but this is basically, sometimes it's kind of misleading. So you might be running 3,000 baud, but you might be sending 12,000 bits per second. Does that make sense? Because what they do is they let more than one bit ride on a carrier. So the carrier is what we do. So what we're trying to do is we're trying to send information through a media. And what we want to do is we want to send a lot of information through a media. So how do we let how many channels do you have coming into your TV? How many cables do you have coming into your TV? How many channels is on that one cable? How do they do that? So when I let multiple signals share the same media, that's what the information travels through. At the same time, we call that multiplexing. So if it wasn't for multiplexing, we'd be screwed. Right, you understand? It'd be like standing in the middle of Jordan-Hare Stadium or Virginia Stadium on the 50-yard line, and your buddies up there on the 50-yard line, and you're trying to talk to them, and there's 75,000 people in there. That's if we couldn't do what? If we couldn't multiplex, well, that's multiplexing. But the problem is I've got to have a way that I can split that multiplexing up, right? So all those people in the stadium are multiplexing. They're all, but we have no way of splitting that stuff up. So what we do is we place that information on a carrier. So how many cell phones is using the air right now? Okay, so how do they split them up? Well, we multiplex. We have a method that we can do what? That we can split them up, right? So my buddy up there on the 50-yard line could take out my phone and call me, and even though the whole stadium's going, I could probably do what? I could probably hear them, right? You understand? So what they do normally is they take the information, they put it on another frequency that we call a carrier. Huh? No, it's a carrier. A carrier is just it's usually a higher frequency that we place information on. And then what we do is now we can set up filtering where we can, So when you get out there on your car radio, when you listen to an FM station, it's got something down there like that 93.7 megahertz. Now what is that? That's the frequency of the carrier. So what your radio does, even though we've got all these cell phones and all this stuff coming by, you can tune it in to one carrier. And then when it comes in, we strip the carrier off, and then we have the information. So doing that allows us to multiplex, right? You understand? And now I have the ability to multiplex. We multiplex all the time, but the problem is a lot of times we don't have the ability to demultiplex. Multiplex, demultiplex. Multiplex. Sounds like we ought to call that a modem. You ever heard of the term modem? Y'all have a cable modem? What is that? What is modem? It's a multiplexer, demultiplexer. So it multiplexes you onto the cable. So now you're on the cable with all these TV channels and everything. And the demultiplexer strips you off, right? You understand, and still have everything else right on that cable at the same time. So if it wasn't for carriers, we'd be screwed. If there wasn't a way that we could come in and multiplexing is easy, right? You understand? So I'm here in the middle of Jordan Hare Stadium or Denny Stadium during a football game on the 50-yard line, and you got 75,000 people there talking. That's multiplexing. But I don't have the ability to do what? Demultiplex. Well, that's what the carrier gives us the ability to do. So as soon as I can come up and pick up my phone and call that person's number, what did I just do? Now I set up a demultiplexer between that other person, which is pretty neat. So just like Ethernet, just like the air. What's flying through this air right now? Yeah, Wi-Fi is flying through the air. All these cell phones are flying through the air. All this is commercial radio stations are in the air. But how can we split them up? Well, we have the ability they place them on a thing called a carrier that we can sense. We can set up a circuit to sense that carrier and do what does what to everybody else. Just blocks them out. So what we do now is, so that when they give you the baud rate now, they're giving you the frequency of the carrier. But what we do now, using different modulation techniques. Y'all have heard of FM and AM. So FM modulates so your signal changes the frequency of the carrier, and then AM changes the amplitude of the carrier, right? And well, if I can combine the two, then all of a sudden I can increase the amount of information I send, because now not only is my signal changing the amplitude, we could also use something else to change the frequency, and we change the phase. So we have a phase shift key, and we have so this is called quad, which is quadrature amplitude modulation, which allows us to put more than one bit of information per baud, which is pretty neat. So just about all your networks. So I've got gigabit Ethernet, or is it sending? No, it's the carrier that can handle that, right? You understand that, which is pretty good. So that answers your question. And then something else. So we have two. We have right now we have Ethernet, industrial Ethernet, and also what they call BFI, 45. We talked about that. So you can interface, you can load more than one driver, right? You understand? You have different Allen Bradley PLCs that you have connected to. And then all you have to do, once you select one of your drivers, if you have your PLC hooked up, then you hit configure, and then you can hit the auto detect, and it'll figure out your PLC, which is pretty neat. Siemens has gone to a new technique, and I don't know about the Factory Talk Allen Bradley, but Siemens, it goes out and finds your PLC. So it's really neat. You can go out there and say, then it figures out what it needs to communicate with you. So more and more as we advance, the more we do it, the less the user has to know. But the first thing you do when you put a new PLC there, the first thing you're going to have to do is establish what? The communication. And then I create a program. What's the first thing I do when I create a program? Select the processor that we're using, right? And if it's a modular PLC, then we have to do what? We have to add the size of the rack and what modules are in each one. If it's a hybrid PLC and I slap another module on there, then we're gonna have to configure the communication with that other module, right? You understand? So it'll be very, very, very simple. So when we come over here and look, so let's